Okay, so we're up in Mathematica now. So the first thing we looked at was the square root of 9 plus x squared.
Yeah.
So this is how you define a function in Mathematica. So f of x with that underscore defined equals this. And then I'm going to plot it from 0 to 10, just so you see what it looks like. Okay. And you see what you expected. Actually, I should have done some plot ranges. But you can see it starts at 3 here. You see that on the y-axis, it doesn't go down to 0.
Yeah.
It goes 6, 4, so that's 3. Your intuition that it grows very slowly in the beginning seems to look right. And then what was our other intuition about this function?
It would kind of stop. It would kind of stop when the derivative reached 1.
Okay, and so what did that mean, that the derivatives seem to be going to 1 on this function?
So it just
it leveled out.
Eventually just looks like a line with a slope of 1.
Okay, and why is that? Like, what's the geometric intuition for that?
Well, you're getting, this triangle is just getting so thin and steep that the side of length 3 matters less and less for really large values of x.
Okay.
So it just starting to look like a line.
Okay, and so Mathematica actually has a function that just does, sometimes derivatives just come with this one little symbol here, that prime. So now I'm going to plot the derivative from 0 to 10.
And
so what do you see here with the derivative?
So it's going up pretty steeply and then leveling off.
It stops at 1.
Okay, and what is it when near x equals 0? What's the derivative down here?
It's pretty steep.
It's very steep.
The derivative itself is steep,
Yeah.
but what is the derivative near x equals 0?
So it's like maybe like 0, 0.1.
Okay, so it's near to
0.
Near to
Yeah.
0. So the derivative itself is near 0. What does that mean about the function itself? Not the derivative. What does it mean about the function if the derivative is close to 0?
So if the derivative is close to 0, it means the function's pretty shallow at the beginning.
Okay, yeah, which is what we saw, right?
Yeah.
So we saw this function being very shallow, very flat near the beginning. And you can see that in the derivative, that the derivative is has a value near 0. Now, you are right to look at this and say the derivative is steep. The derivative function is steep, which means the derivative itself is increasing very rapidly. And it increases all the way up and then eventually kind of flattens out when its slope is equal to
1.
1, when the slope of the function is equal to 1. So the derivative flattens out around 1. Now, the second problem I gave you is an example of something called the differential equation. So you are being asked to solve, remember y prime is what that means, derivative?
Yeah.
The derivative equals the function. And the function at 0 equals 1. Okay?
Mm-hmm.
And then, so I'll put that in. And then, what does that say our function is actually?
So e to the x.
E to the x.
Huh.
Hey. What? E showed up. And I'll plot, originally I was going to plot it from 0 to 4, but you know what? I'm going to plot it from -4 to 4. So you can see both sides of this.
So that's what we thought. It starts out really, really shallow and then
Sorry, it's not quite
steep.
on camera.
Steeper and steeper.
All right, there we go. So what do you see as you go positive?
It starts kind of a shallow slope, and then it starts to get really, really steep slope.
Yep. And this is even misleading you a little bit on the slope because the x-axis distance, this is going from -4 to 4, and this is going from 0 to 25. So this distance is 8, and this distance is 25. Right, so we know the slope at 0 was 1, because that's how we set up the problem. But you're right, it still looks pretty shallow and goes to infinity very fast. What about when you go to the left as the x values get negative?
It's really, really shallow and is approaching 0 pretty fast.
Yeah, how fast?
It's actually very fast.
It gets there by -2.
Yeah,
Gets there.
it looks like even at -2, this is already at 0. But let's zoom in. Let's plot it from, instead, let's plot from -4 to -2. And let's see what that looks like.
So it's not actually there yet.
It's not actually 0, but
it's like 0.14, and even at 3.5.
At minus 3.5.
Minus 3.5.
Why does it go below there?
Well, because this is not quite 0. See, it's going down by about 2 100ths every tick. So it's going from 8 to 6 to 4. So this is more like 0.02. You see that? So this isn't 0, 0 would be down here. And I can also plot from like minus 6. Am I on camera here?
Yeah.
Okay.
The function's not quite on camera.
It seems
I can plot it from minus 6 to minus 4, and look, I'm down all the way to like minus 0.005.
kind of looks the same function, but it's just really small.
You're zooming in each time.
Yeah, isn't that amazing? When you zoom in, it starts looking like that same, what's called exponential growth, almost no matter where you look.
Kind of like a fractal.
Sort of.
Yeah.
Yeah, sort of like a fractal. So it's pretty neat. So these are some very basic ideas in calculus. And it's actually fun to start thinking about how do we describe things that are moving, and how do these graphs help us understand that movement. So even just these simple ideas, you guys were able to get some nice results. High five. Good job, guys.